research knowledge graph. It will be presented by Professor Auer. I will just briefly read a few information about Professor. So Professor Auer was appointed Professor at Data Science and Digital Libraries at Leibniz University at Hanover, and he's director of the Technical Information Library from 2017. Professor Auer has made important contributions to semantic technologies, knowledge engineering, and information systems. He is the author and co-author of over 100 peer-reviewed scientific publications. He has received several awards, including an ERC Consolidator grant from the European Research Council, and so on, as WUSA 10-year award, and so on. He has led several large collaborative research projects, such as the EU Horizon flagship project Big Data Europe. Also, he is co-founder of some high potential research and community projects, such as the Wikipedia semantification project DBpedia, the open courseware authoring platform, slidewiki.org, and the innovative technology startup essensa.com. A professor also was founding director of the Big Data Value Association, led the semantic data representation in the industrial international data space, and also he is an expert for industry, European Commission, as well as for W3C, and a member of the advisory board of the Open Knowledge Foundation. So I'm not going to read the abstract of this presentation, so I'm going to give the microphone to Professor. I believe he will much better explain the main point of his presentation than I can do that, of course. Now I'm going to stop sharing my screen. So Professor, the microphone and the audience are yours.
Yeah, thank you very much. I'm sharing my screen and I hope you can all see my presentation.
Yes, I can confirm that we can see that.
Perfect. Yeah, thank you very much, Dragan, for the invitation. And I'm really excited to be here with all of you. Of course, I'm a bit sad that we cannot be together in Amsterdam as originally planned. I was actually looking forward to that, to the coffee breaks, to the discussions. But I think it's really great that we can at least gather virtually and I can present you some of the things we are working on. So I would like to start a bit by drawing a bit larger bow. Maybe initially I show you some pictures from Hanover. So you can see there in the background the castle of one of the princes of Hanover, which is now the university, the Leibniz University of Hanover, where also Gottfried Wilhelm Leibniz was actually working in Hanover. And in front is more building from the 70s, 80s. That's the library of the university, but also an information center for science and technology called TIB. And I'm the head of TIB. I'm also professor at the university. And you already see there is a lot of Leibniz, yeah. And I would like to clarify a bit what's the relationship between TIB and the university with a small knowledge graph, introducing to you already the concept of a knowledge graph. So we as TIB, we are the library of the Leibniz University of Hanover. And we are also member of Leibniz Association, which is one of the 4 big research associations in Germany, in addition to Fraunhofer, Helmholtz, Max Planck. So both actually share the namesake, Gottfried Wilhelm Leibniz. And interestingly, Leibniz was born in Leipzig in 1646. So that makes the confusion perfect. And of course, there's also these famous Leibniz cookies, which you might remember maybe from your childhood. So 100 years ago, it was popular to name famous delights after famous people like Leibniz. And what you see here is already a small knowledge graph where we have entities like the university, like the TIB, like Leibniz Association, Gottfried Wilhelm Leibniz in person, or the cookies, and the relationships between these entities. And that's a knowledge graph clarifying the relationship between different entities and organizations, persons, in such a graph notation. And I would like to tell you a bit more how we can use that for science. In order to do that, I want to start a bit larger by asking the question, how did information flows change in the digital areas in different domains? So if we look, for example, at mail order catalogs, that's what you see on the very left. That was a famous mail order catalog, Quelle, which was maybe one of the reasons why the iron wall was falling, because people in East Germany, I myself from East Germany, we were really excited about all these cool products you could see in this catalog. That completely disappeared. No one orders today from mail order catalogs anymore. Similarly, we don't use street maps. Maybe 10, 15, 20 years ago, you remember you had to buy street maps when you wanted to get from A to B. Every year there were updated maps available. Similarly, phone books, yeah, which were quite popular, or encyclopedias, which were used to represent encyclopedic knowledge and were printed every year. So in these different domains, the information flows pretty significantly changed, right? So we order nowadays products on e-commerce platforms like eBay, like Amazon, or here you see a screenshot on the upper left of Idealo, a price comparison website. We use for navigation map services like Google Maps or OpenStreetMaps. In terms of encyclopedias, we have Wikipedia. For communication, we use Skype or WebEx or Zoom, like now. So these kind of information sharing, communication, publishing has dramatically changed in different domains. And it's not just that the analog way was pseudo-digitized in form that we have a PDF version of a mail order catalog or a PDF version of a map, but we really have developed services which exploit and leverage these digital possibilities, which means you can zoom into the information, you can drill down, there is more dynamics. The business models behind it have completely changed. There is more focus on data, on interlinking data and services, on search in the data. We can integrate different data sets, crowdsource information, and data curation. These all play an important role, and these are completely digital-born developments, maybe, for these domains. So now, what about scholarly communication? How does information exchange, information flow in science and research work today? If we look how it started in the 17th century, you see here a screenshot, or actually a scan of the Philosophical Transactions, one of the first scientific journals. It was pretty much the same and stayed pretty much the same over the centuries. Yeah, if we look for how publications nowadays look like, they are a pseudo-digitized version of what we were doing for hundreds of years. We basically create static PDF documents and exchange them by email, or you can download them from web services. But this is comparable as if you would use a phone book as a PDF version, or you would use a mail order catalog via PDF. No one would use that today because there are these digital-born services for information exchange in these other domains. But I would say we in research, we work with really antique methods, and we didn't really digitize science, research, and scholarly communication. So there are a number of problems caused by this lack of digitization. So we have a monopolization of commercial actors. We have a reproducibility crisis. Majority of experiments are hard or not reproducible. We have a proliferation of publications. The publication output basically doubles within a decade and continues to rise. We have also a deficiency of peer review. So the quality of peer review is deteriorating, and there are also phenomenons like predatory publishing appearing, for example. So I think that scholarly communication is in trouble, and we have a big problem. To illustrate that maybe a bit more, if you look at the proliferation of scientific literature, here you see an overview how it has grown from 2004 to 2014. Yeah, so it almost doubled worldwide the output of papers, of scientific articles. And this is only the science and technology domain, science and engineering domain. It's not so much because we in the Western world published significantly more. If you look, for example, in United Kingdom or also Germany, it increased by 20–25% probably. But it significantly increased in countries like China, where it quadrupled, or India, Brazil, Russia, which entered this scientific world and followed these practices of publishing and focusing on quantity and not always on quality. The reproducibility crisis I mentioned, there was this famous study by Monia Baker in the Nature, published in Nature, where she surveyed 1,500 scientists and found out that 70% of them actually failed to reproduce at least one other scientist's experiment, and 50% failed to reproduce one of their own experiments. And that includes, for example, also myself. Yeah, in computer science happens quite often that you do some experiments with some software environment, and after 2–3 years, the software is outdated and you cannot really port it to the newest version, and then it's difficult to reproduce these experiments, even if you have the best intentions. And you also see that in different domains, of course, it varies a bit, but we have really a problem with making science more reproducible. Often also one of the reasons is that not all information is contained in a paper to really reproduce the experiments which were presented. And my impression is a bit that we have a lot of duplication and inefficiency in scholarly communication. So if we look a bit at other domains, for example, a building, how could you build such a complex structure if you don't know what the individual parts are? So you really need to identify, you need to exactly know how they fit together, what the measures are, what the characteristics of these different parts and relationships are. And in science, we also need to build a complex knowledge structure or some kind of knowledge base. And also we have this requirement, of course, to fit different pieces, bits and pieces of knowledge together. But my impression is that currently it's hardly fits together. Everybody uses his own terminology. We have very vague definition of research problems. Approaches are not well defined. Methods, characteristics, evaluations, all this is relatively vaguely defined in the papers and also not clearly identified. We don't have identifications for these things described in the papers. Of course, we have identifiers for the papers itself, like DOIs, digital object identifiers, but not for these parts and for the actual research and the artifacts of the research we are doing. So summarizing, we have a lack of transparency. Information is hidden in text and unstructured text publications. We have a lack of integratability. We need to fit different research results together. Also, machine assistance is hardly possible. We have unstructured content, and this is difficult for machines to make sense of and to understand and to process. Yeah, everybody talks about AI and machine learning. But in this pile of papers, it's impossible. It's already for us humans almost impossible to make sense of this flood of papers. How could a machine assist us there? Of course, full text search is possible. We can do keyword search, but more than that is hardly possible. And we would like, for example, to use something like question answering or more structured semantic approaches for machine assistance. And that's difficult or almost impossible with the current representation of scholarly communication. Similarly, we have problems with identifiability. We can identify metadata. We have ORCIDs to identify researchers and DOIs for identifying papers, but we need to identify the actual artifacts, yeah, the approaches, the problems, and also describe the connection between them. We have a problem with collaboration. There's this one brain barrier. The different bits and pieces from different publications don't fit well together. and scientists can hardly get an overview. They often look for the needle in the haystack, basically. So to illustrate that a bit, I want to give you some example. If you look in our library portal for the genome editing method CRISPR, you find 9,000 results. And that's because we as TIB don't focus on life sciences, and that's a biochemical method, so you only find a bit of chemistry covered. If you do the same search in Google Scholar, you find already almost 250,000 results. And if you want then to know how good is this method with regard to precision, safety, cost, what specifics does it have when you want to apply it to insects, or who has applied it to butterflies, you are basically lost in this huge amount, in this heap of information, and you need to do years of research in order to answer these questions. So how can we fix it? It's a bit depressing. How can we actually solve this problem? And there was this vision of Vannevar Bush, this vision of realizing something called MEMEX. This was shortly after World War I, when he published this visionary article in The Atlantic, describing an apparatus which magically, I would say, displays information at the fingertips, and under the desk, basically, the information is organized. I would say at that time it was a bit esoteric, but nowadays we actually have the ingredients to realize that, to realize a knowledge base which can assist scientists and researchers to do science. And what we need for that is we need to identify first what are the research problems, what are definitions, what are the research approaches and the methods. And we also need to integrate artifacts in addition to publications. We have data. We have heard in several talks how important research data is. Open science, software plays a big role in computer science and engineering. We have images, audios, videos, we have ontologies, and all these artifacts, they need to be linked also with domain-specific concepts. If you look in the different domains, you have, for example, in mathematics, definitions, theorems, proofs, methods; in physics, experiments, data and models; in chemistry, substances, structure and reactions, and so on and so forth. And what we need is to identify all these concepts and link them, establish the relationships between them to clearly identify and define how are they related, how can they be integrated, and then to allow machines to assist us in processing this information. And how can we realize and implement this? There are the linked data principles, and you see here Tim Berners-Lee, who is one of the advocates of this linked data principles. And he claimed, or he coined this linked data principles, which were about identifying things in the data, using your eyes to identify things, then making them also retrievable, that you can then look them up on the web, use the RDF resource description framework for representing information about the data, and also include links to related things. And I would like to illustrate with one small example how this actually works. If you look at this conference, which we are currently participating in, ICTE SSH, so we can say that Science 2.0 organization organizes this event. We have such a subject predicate object statement. And we can then use the object as we do in natural language. Usually when we have a sentence, we can use the object of one sentence as a subject for the next sentences. So we can indicate that the event starts on the 29th of June in 2020, and it takes place in Amsterdam. And this is a small knowledge graph where we have where each individual fact or statement follows the subject predicate object paradigm. And you can imagine there can be further information. We can attach more information about Amsterdam or about Science 2.0 and so on and so forth. So such a knowledge graph can organically grow, can become bigger. And the nice thing is that this knowledge graph is on the one hand human readable, so we can understand what's going on basically when we look at such a graph, but also machines can understand. And that's what you see here on the button. It's serialized in RDF triples, and these triples can be relatively easy be understood by machines. And then also be integrated from different sources if we have information from different sources. So I have here an example from industry, an industry example, basically about the company DHL, and you can describe also in such a knowledge graph information about companies, their headquarters. You can attach labels in different languages, as you can see here. That's the base idea of linked data and knowledge graphs. And knowledge graph comprises a large variety of information. So instance data, schema data, metadata, taxonomies to categorize entities, also links between internal and external data sources, mappings to other systems and databases. So that's a definition of knowledge graph to comprise basically these three aspects, not only metadata, but also the data itself and also vocabularies and schemas to structure the data. You can see on the right-hand side an example from DBpedia, which is a large knowledge graph which we extracted from Wikipedia, comprising encyclopedic knowledge about people, organizations, places. Here in that example, for example, Bob Dylan, and information about that Steve Jobs is a fan of Bob Dylan, and so on and so forth. Meanwhile, a lot of organizations are building knowledge graphs. A lot of companies are building knowledge graphs to integrate their enterprise data and enterprise information sources. Also in the digital library area, for example, there's the European Digital Library Europeana, and a number of other libraries are quite active. In the life sciences, we have a lot of traction in building knowledge graphs for representing life science information, and so on and so forth. And now the question is, how can we apply this concept for scholarly communication, for research information? And I would like to illustrate that with a small example before I show you our open research knowledge graph. So here you see a paper, a chemistry example, the CRISPR-Cas application of this genome editing method to Lepidoptera, which are butterflies. It's a Latin name for butterflies. And such an open access publication, for example, could be accompanied not only with metadata, like about the author, but also what research problem is tackled in this particular paper. What methods are used, here in that case, CRISPR-Cas. What are the methods applied on, in that case, on Lepidoptera, and where can I find the experimental data? All this information basically could be curated in some kind of a form and then represented in a knowledge graph and create a small snippet of a knowledge graph. And when we integrate lots of these descriptions together about different publications, we actually build such a knowledge base describing scholarly communication and scholarly contributions. So we can then use the knowledge graph for exploration and question answering. Yeah, for example, we can ask, how do different genome editing techniques compare? And we can parse this question. We can understand the named entities and the relations in the question, build a formal query operating on the knowledge graph, and then actually executing the query and rendering the result to the user. I guess many of you have already used services like Google Now or Apple Siri or Amazon Alexa. They basically follow such a paradigm, yeah, question answering paradigm, but that only works when you have a structured knowledge base, when you have your knowledge, your data, your information organized in a coherent way in a database or in a knowledge base. And I think we need to do the same in science and research in order to make sense of this wealth of information out there. And as a result, this question about genome editing methods, comparing them, could then render a table, for example, to the user, showing how the site specificity, the safety, the ease of use, the cost, and the speed of these different methods is when compared to each other. Okay, so this was a bit illustrating how this approach could work. And now I would like to show you a demo, how such an open research knowledge graph can be built. And maybe I switch to my browser session, and I hope you can follow me there. So I just... So, and here you see an example, a comparison of scientific papers. Basically, we see one important question is for example, right now affecting us all with the coronavirus, is the reproductive number of the coronavirus. And that was initially a big research question. I think meanwhile it's relatively solved, this question. So the question was, what is the reproductive number of the coronavirus? And there were a number of papers. So we actually integrated here 31 papers, which all aimed to tackle and to answer this one research question about the reproductive number of COVID-19. And what you can see here in this table is basically each column contains a reference to one of these papers. So we have here a first study, we have the date when the study was performed, in February, in January and February already. We also have the location that was done in Singapore, and then we have this R0 estimate. So this is the value of the reproductive number, basically how many people get infected by one previously infected person. Here in this first study, the authors determine a value of 1.97. And then they have a 95% confidence interval, so it lies between 1.45 and 2.48. Then there's also some, here in that case, there's no information about the method and the approach they use to determine the R0 value, but for other publications, we have this actually. And as you can see, there were a number of studies, and only by getting an overview of these different studies, you can actually say where probably the real value of this R0 value is. And you need to read a lot of these papers, but an even better way is to have such a systematic, structured overview in a tabular comparison, for example, like here, where you can then browse these different articles, and you can very quickly see what number the different authors conclude the R0 value is, yeah? And you can get a quick overview basically on the research for this particular research problem, also on the locations where it was performed, on the time frames where it was done, and that gives you a bird's eye view on this research problem and the most important information and the comparison between the different studies in this area. You can also visualize it. For example, if you click on, there were some visualizations linked there, and we can then see here, since the information is represented in the knowledge graph, we can actually create a scatter plot, or we can create a bar chart, and we can even indicate also in a combo chart, for example, the confidence interval, and you can get an even more condensed representation of the research results. And these visualizations, they can be created automatically. They basically operate as a query on the underlying data set, on the underlying knowledge graph representation, I have to say here, and then they generate a condensed representation. And once more studies are added, the visualization also automatically is updated. And let me maybe show you one particular example. We can click on one study here, and then you see actually the description in the knowledge graph of this particular study. So we have here the research problem indicated, which is COVID-19 reproductive number. And then we have the contribution data, we have the confidence interval indicated, we have the approaches which are used, we have the location, and you see here the location links to another resource, in that case to China. We have the methods described here, we have the R0 estimate, and the study date indicated. And we can also edit this if we are signed in. You can basically then also add more values, for example. You can add more properties. We can add another property. And while you are typing, it suggests existing properties already from the knowledge base so that you don't create new representations, that you basically reuse existing properties. And then you can also link to existing resources. So you see here that it actually, for example, when you enter Singapore, it offers to directly link that to Singapore. So that allows to create and to crowdsource such semantic representation. So the idea is that, of course, some things are automatically extracted from the papers, but other things are also contributed manually by the users and by the community to create such semantic representations of the articles. And you can then also look at the graph view. So you can open the graph view. You can then see here there is metadata, of course, but we also have the different contributions, and we can click on one contribution, and the graph basically expands and shows us more information about this particular contribution. And here we see this number 2.24 and the confidence interval. So these are the important values as outcomes from this particular study. Yeah, let me maybe also show you some examples. We actually have prepared some examples also from social sciences. You might ask, what does this have to do with my area of research? And of course, in some domains, it might be easier, and other domains a bit more difficult to apply this concept of creating such structured semantic descriptions. And here you can, if you go to the ORKG homepage, you can actually see different research fields and the papers which we have already in the research fields. And you can also look at these kind of comparisons which we have created for some research problems already. And then you see for some selected research problem already a number of comparisons which compare different approaches. So, and to show you also some example from social sciences, we created 3 here. And of course, you might maybe say, yeah, that looks very similar to surveys and review articles. And exactly that's one idea, that we have a platform where we can create more dynamic, more evolutionary reviews and surveys. And we imported 3 surveys from the social science domain in the open research knowledge graph. Here's, for example, one a comparison of psychotherapy for depression studies, 15 studies which are compared, and this originates from this reference. What you can see here, who have already done the work of creating such a tabular comparison. But the difference is that in the open research knowledge graph, you can actually curate, you can add further studies to one particular research problem. You are able to create it in a collaborative manner. Everybody can participate. It works a bit like a wiki. And here you basically then have such a structured overview of the different studies, of the problem they tackle, maybe of the particular disorder they focus on, what recruitment strategy they followed, or what setting the experiment, the study was performed in, and you can get a quick overview of different studies in one particular area. And there are some more examples here: psychotherapeutic inventions in cancer, and a similar comparison there. And of course, our idea is not just to create such tabular comparison, but to create in the background an interlinked, highly semantically represented knowledge graph. And we would be very interested to collaborate with some of you in building such a knowledge graph for social sciences, and maybe adding more research in this area, creating such comparisons and also visualizations. Yeah, these comparisons are maybe only the first step. Later you can visualize it, and you can also integrate information from different research problems and gain new insights by running queries, by answering questions over this knowledge base, which we have there in the open research knowledge graph. So, yeah, and with this, maybe I would like to come slowly to an end of my talk. I hope we have some time for discussion. At TIB and Leibniz University of Hannover, we have a quite large team of people working on this open research knowledge graph. It's a strategic initiative which we want to further develop in the next years. We know that this is a not a short-term project, but a major effort which requires probably a lot of collaboration. That's why it's also open science, it's open data, it's open source, the software, everything is developed in a very open way, and we want to collaborate and integrate this with work also from other groups. So concluding, I think we need to reinvent scholarly communication, and knowledge graphs are well suited to capture research contributions in a structured and semantic way, making them both human and machine readable, which I think is a requirement. With the Open Research Knowledge Graph initiative, we aim to establish a registry for research contributions in different areas and different scientific domains. As I said, we have created some initial examples in the social sciences, but this is very early, and it needs to be taken further, and we would be really happy to collaborate with some of you on that. And I think using such a knowledge graph, we can synergistically combine human, expert, and machine intelligence. And this is, from my perspective, the major challenge. There are, of course, others who build already knowledge graphs for research. They focus primarily on metadata or on fully automated extracted information, and there usually the precision and the recall is not sufficient. I think we really need to integrate human and machine intelligence and collaborate. Both need to collaborate synergistically in such a knowledge graph. Yeah, and that's what we are continuing to work on. Please join us. You can join our mailing list or the Open Research Knowledge Graph project. We also have now started the concept of observatories for different domains. So organizations who want to create a part of the graph are invited to run such an observatory, and we will then also acknowledge these contributions. Yeah, thank you very much for your attention. And I hope we have a few minutes left for discussions.
Okay, thank you very much for a very interesting presentation. And I notice we already have 10 questions in Q&A here. I'm not sure whether you can open Q&A box.
Sure. Yeah, so shall I read the question?
Okay, maybe we can start with the question, which is with the highest number of the likes, which is on the top of the list.
Yeah.
Lucas van der Meer.
How do you deal with the
massive variety of possible metadata on research methodologies and outcomes, example between fields? Who created the metadata standard? So also I can extend here the question, different vocabularies could be a problem in the meaning. For instance, you provided us, thank you for that examples related to this conference and who is organizing this conference. But in one RDF, it could be called is organized by, in some other, maybe some other term could be used for that link between two entities. Yeah. So who is responsible for the standardization of that?
And my answer to that is it can only work with the community. Yeah. So because research is so diverse, so heterogeneous, I think there cannot be one institution who is standardizing that, but it needs to emerge from the collaboration. And that's the approach we want to follow. There are some examples where it works already. If you look at Wikidata, if you look at OpenStreetMaps, these are examples of really large knowledge graphs which organize vast amount of information, and where all these properties and vocabularies basically emerge from the collaboration. And that's what we also want to establish, that the community curates the knowledge by themselves. Of course, it might be that in the beginning there are maybe duplicate properties and different descriptions, but then we need to support the evolution and the alignment so that you can change and you can revise the description to align this and to harmonize that, so that we come to a more harmonized and more standardized description of the research. And that's a bit what we aim for, what we want to establish, because every ontology you would develop would already quickly be outdated.
Yeah. Yeah, that's the problem. We have actually more than one ontology, and then we have to select the right one. Yeah. Okay, so we have 9 questions more, so maybe we can select one or more to answer live.
Yeah, the next question is actually directly related also to that topic. Do you use ontologies? Of course, we use some ontologies, but not in the sense that they are fixed. You can actually use any kind of resources in the Open Research Knowledge Graph. So you can use any classes or properties you want. So you are open to do that, but it's like relatively flexible. You can add also new properties, create new ones. So we want to have a dynamic, evolving system and not a fixed ontology which is dictating everything, but some dynamic system.
Thank you.
So next question was, are we supposed to download already published research papers? I don't completely understand what you mean with download. Our idea is to describe already published papers, of course, but we also don't need to describe everything, because usually for one research problem, there is maybe dozens or sometimes maybe 100 of papers are relevant for describing the contributions to this research problem. And of course, that would be nice to be added to the Open Research Knowledge Graph, but it can be done incrementally, step by step. Next question is about how this relates to the OpenAIRE research graph. And of course, we are discussing this with OpenAIRE. It's a big difference because, of course, there are a number of research graphs or scientific graphs there. For example, there's also one by Springer Nature called SciGRAPH. I think there's Microsoft Academic Graph. But all these graphs, they are basically focusing on metadata. They focus on publications and authors, maybe sometimes on topics, on journals, on conferences, but that's something we don't focus at all in the ORKG. We want to describe the research published or inside the publications. Yeah, so we want to go much deeper. That's why both and all these initiatives are a bit complementary. So we don't focus on metadata, and these other initiatives usually don't focus much on the content of the articles, and that's what our primary focus is.
Okay, maybe you can select one more question to answer before we complete this session. So the next one, according to the number of the likes, from
that's about discussing with publishers. Of course, I've presented that to a number of publishers already. They're very interested, and we will continue that. Of course, we're also still in an early stage with the ORKG. It's still relatively small amount of content which we have in there. We also need to improve the usability. There are a number of open issues which we are working on, but we will now intensify these discussions with publishers. And in particular, I fully agree that open access repositories are maybe the most promising collaboration partners for us there.
Okay, and we have one raised hand from Irina Dokhnov. Would you like, Irina, to comment?
Yeah, thank you very much. Thank you for the wonderful talk and really great topic. My question is about linking with blockchain technologies like Blocksberg or Ethereum. Do you have any ideas or approaches already implemented or in planning?
No.
Okay.
No, yeah, blockchains. To be honest, I'm not very interested in blockchains. I think it's a lot of hot air there. And I think you can build, the web is a decentralized system, so you don't need blockchains to make something decentralized. So currently we didn't do anything related to blockchains. Of course, I have some colleagues at TIB. There is Lambert Heller. He's working on some blockchain stuff, and we might look into that, but currently we haven't done anything yet there. Sorry.
Okay, thank you.
Okay, so I think we are at the end of this session. So Professor Auer, thank you very, very much for really nice presentation and for discussing with us, for answering on a few questions.
Thank you for the invitation. It was really nice.
Thank you for accepting to be part of this conference. It's not realized as it planned to be in Amsterdam, but at the end, I think it was successful and useful for people to listen to some nice presentations, including yours, of course. If you have time, of course, you can stay in the call. You can even try to answer on some questions in text or mode. There is also that option here. After this session, we have a 15 minutes break. And after that, we will have a sponsor session